So we have shown that the new j is the expected number of visits to the state j in the first excursion of the Markov chain. This is equal to this quantity here. So we have shown this with the help of the Markov property. The main step was the Markov property. So essentially what we have done so far to prove this is the penultimate step analysis and Markov property. That's all we have done. Okay, so now note that just by putting n equal to 1 equal to m, we get that this is just the sum from m from 1 to infinity. Same thing, you just put n minus 1 equal to m. So that will give you this is x1 up to xm minus 1 not equal to y, xm equals k and pkg. Now that is just like the previous argument. This is just m equal to 1 to infinity of starting from I, probability pi, first return time to 1, strictly bigger than m, and xm equals k. So obviously first return time is strictly bigger than m would automatically imply that xm cannot be I, but xm has to be some k, that k is here. So inside this, so this whole thing is basically this event is same as this event. This is basically what we have done before, same thing. So tau I1 bigger than m just means x1 cannot be I, xm minus x2 cannot be I, all the way up to xm minus 1 cannot be I. Also xm cannot be I, but xm is already k here, so therefore that has already been ensured. So therefore you have to ensure that these are all not equal to I. So these two events are the same. Okay. So now this event now can be written therefore as, so pkj can be kept here. There is no m here, so pkj can come here. And this is basically expectation of the sum of these indicators. So expectation of sum of the indicator is just the sum of the probabilities. So therefore, this is equal to this. So therefore, we have shown that nu j is equal to this quantity. And this is just nothing but, first of all, okay, nothing but this quantity. So there are two things I have to ensure. One is this Pij is nu I times Pij. Now remember, nu I was 1 because the quantity inside the expectation is 1 with probability 1. Therefore, the expected number of visits to I in an excursion to I, is of course 1. So therefore, nu I is 1. So using that, we can write the nu I times Pij. And here we have Pkj times. This quantity is just sum of same thing, except that instead of writing this, you just write m equal to 1, 2, all the way up to tau I1 minus 1. So this, this we have done this calculation before. So m equal to 1 to tau I1 minus 1 is essentially m equal to 1 to infinity with an extra indicator that m is strictly less than tau I1. Okay. So therefore, these two quantities are the same. Now note that k is not equal to I. So since k is not equal to I can as well start the sum from 0. Because starting from I, xm is definitely cannot be k. Starting from x0 cannot be k because starting from x0 is I, which is not equal to k. So therefore, for each k, which is not equal to I can definitely also put 0 in this sum. We are just adding, by adding this extra term of indicator x0 equal to k, we are just adding a 0 here. Because the Markov chain is starting from I, therefore x0 is I, and therefore x0, indicator of x0 equals k is actually 0 because k is not equal to I. So therefore, this quantity and this quantity are the same. The expectations are the same. Now, what is this quantity? This quantity is something we know. This is just nu k. This is just our nu k. So therefore, what we have shown is that nu j is nu I pij plus nu k times pkj, where k runs over all the states except I. So therefore, this is just sum over all the states of mu q, which proves that nu is indeed an invariant measure for the Markov chain. So the proof was long, but as you could see, the main steps for the proof was, firstly, to do penultimate step analysis. And the penultimate step had to be something different than I. That's why we had a sum over all the states other than I. And then we had to use Markov property. Penultimate step analysis and Markov property. These are the two main steps that we used in the proof. The rest was just, going through the calculation. It's a bit long, but it's just usual calculation. We have done such calculation many times, so it should be easy for us. Okay, so this proves that mu is indeed an invariant measure when I is recurrent. Now, when I is positive recurrent, we'll have to show that sum of these nu j's is finite. So that normalization will give us a stationary distribution. So we claim that the sum of these nu j's is actually strictly positive and finite. Why is that so? Now, sum of this nu j would be sum of these quantities. Nu j is this quantity. So sum of these nu j is sum of these quantities. Now expectation, sum of expectation is expectation of sum because everything is non-negative. Okay, remember everything is non-negative here. So therefore, expectation, sum of the expectation is expectation of the sum. Again, since everything is non-negative, these two sums can be interchanged. Okay, that's thanks to the Fubini theorem, but let's not worry about such things. Since everything is non-negative, we can interchange these two sums. Okay, now look at the inside sum. The inside sum is essentially sum over all j in S, xn equals g, indicator of that. For a fixed n, xn will be exactly xn will be equal to j for exactly one j and 0 for all the other j's. So therefore, this sum of this indicator, this red quantity here, is always going to be 1. Okay? For every fixed n, xn will only take one of the values in this state, right? At a time. So therefore, one of these indicators, exactly one of these indicators would be 1. All the other indicators would be 0. So therefore, this sum inside this red sum here will give you 1 all the time, identically equal to 1. So therefore, this is just sum of 1s running from 0 all the way to tau y1 minus 1. So you have tau y1 many 1s. So therefore, this is the expectation of the tau y1. And since I is positive recurrent, this expectation is actually finite. So therefore, this is, and also it's positive because tau y1 is by definition bigger than or equal to 1. So it's a strictly positive quantity. So it's actually bounded by below by 1. So expectation of tau y1 is at least 1, in fact. So therefore, it's strictly positive also. Okay, so this proves that the sum of the nu j's is finite. Not only that, the sum of the nu j's is actually expected first return time to I. So combining everything that we have shown so far, what we have actually proved is that if you start with the recurrent state and you define nu j to be the expected number of visits to j between two successive visits to I, or expected number of visits to j in the first excursion to I, whatever you call it, this is also equal to this quantity here. Then this nu is an invariant measure of the Markov chain. If further I is positive recurrent, then pi j, which is a normalized nu j, which is nu j over sum of all the nu j's, which is essentially expected first return time to I. This quantity is actually a stationary distribution of the chain. So this is the theorem that we have proved. So this just tells us that if we have a recurrent state, we can get hold of an invariant measure. And if we have a positive recurrent state, then we can get hold of a stationary distribution. But of course, the question will remain whether the stationary distribution is unique or not. And we will see next time that the stationary distribution will be unique when the Markov chain is also irreducible. If the underlying Markov chain is irreducible and the state I is positive recurrent, then there will exist unique stationary distribution. On the other hand, if the Markov chain is irreducible and I is actually recurrent, so it's a recurrent Markov chain, therefore, then we will be able to show that, of course, this nu j will still still be nu will still be an invariant measure, but we'll actually be able to show that any invariant measure would be a constant multiple of this invariant measure. So in other words, up to a constant multiple, invariant measure is also unique, as long as this is recurrent. It's irreducible. The Markov chain is irreducible, and the state is recurrent. Also, one more issue that we'll address next time is that we haven't shown that these nu j's are actually all strictly between 0 and infinity. We have only shown that in the case when I is positive recurrent. In fact, the sum is strictly between 0 and infinity. Therefore, each nu j is strictly between 0 and infinity. Under irreducibility, we'll show that each nu j is strictly between 0 and infinity. We'll do it next time. So, as you also another issue that I have only told you verbally, but I think it's good to write it down. If the Markov chain is irreducible and the state I is positive recurrent, then pi j defined above, okay, is the long run proportion of the chain hitting the state chain. So what proportion of the time the Markov chain will hit the state chain if you run the Markov chain for a very long time. Okay? This will make pi a very good candidate for the stationary distribution. This also needs to be justified. We'll see this next time.